Let's take a look at the series I wrote here on the right, starting with the harmonic series, the series of the reciprocal of the positive integers. We all know that this series diverges, and the reason that it diverges is that even though the n's, the 1 over n, go to 0, the terms of the series go to 0 as n goes to infinity. The terms of the series are not going to 0 fast enough. So they are not going to 0 fast enough, means that the partial sums keeps getting bigger and bigger. So the partial sums here will, the sum of the series will explode to infinity. On the other hand, we know that when we take the alternating version of the harmonic with the alternating plus or minus sign, then that this series converges, the alternating harmonic converges by the alternating series test. Okay, so here we have the well-placed minus signs stop the partial sums from exploding to infinity, actually make them converge to a finite limit. So here we have the alternating harmonic converges, the harmonic diverges. On the other hand, if you take a series like negative 1/2 to the n, so this is non-negative power series of non-negative powers of negative 1/2, 1 minus 1/2 plus 1/4 minus 1 over 8, etc. So this is an alternating series, of course, and it converges either by the alternating series test, again, because 1/2 to the n, the an term is decreasing and goes to 0, or just even before the alternating series test, this series is geometric series whose r equals to negative 1/2, and if absolute r is less than 1, we know that the geometric series converges. So here the alternating series converge, but the non-alternating version also converges. If I replace, if I get rid of the negative signs and I take just plus signs, so I take the series of non-negative powers of 1/2, then the series also converges. It both converges in the alternating version and the non-alternating version. Okay, so for this we have, for this reason and for others, we introduce this very important definition. Given a series, this series could be have mixed terms plus or minus, could be, it doesn't have even to be alternating, it could, because the mixed plus or positive and negative terms do not have to happen uniformly like this. So any series whatsoever is called absolutely convergent if the series of absolute values, absolute value of the terms, converges. So if you replace all the minus signs appearing by plus sign, the resulting series converges. In this case, we call our series absolutely convergent. So by this definition here, we have that the series on top here is absolutely, series of these terms is negative 1/2 to the n. This is absolutely convergent, but this is not absolutely convergent. Okay, so now absolute convergence or absolutely convergent series are very nice to work with because of this property, this theorem. Absolute convergence implies convergence. So absolute convergence is a stronger property than convergence. Okay, so so it means that if you know that a series is absolutely convergent, you know automatically that it converges. So for example, suppose we didn't know that this series converges, just by knowing that the corresponding geometric series, non-alternating geometric series, so when we get rid of the negative signs, we put positive signs, this series converges, then we can conclude automatically that the series above converges. No need to invoke the alternating series test or to invoke that it's another geometric series with r in an absolute value less than 1. And moreover, all the tests, the comparison test, the limit comparison test, the integral test, the ratio test, the root tests are all tests for positive series, so they are all tests for absolute convergence. So it's a good strategy, by this theorem, it's good strategy when I give you a series that you test for absolute convergence first. So because when you're testing for absolute convergence, you remove all the negative signs, you get a positive series, and then you can use all these tests, whatever is convenient for the series at hand. And if you manage to conclude that the series is absolutely convergent by one of these tests, then by this theorem, the series, the alternating version, or the version with mixed signs plus and minus, that does not have to be alternating, will be also convergent. On the other hand, if you cannot establish absolute convergence, like in this case, we cannot establish absolute convergence, we know very well that if we take if we get rid of the negative signs and make them all positive, then the series will diverge. Then we have to examine the convergence of the series with mixed plus or minus signs, and for that we have less tests to rely on. Maybe the alternating series test, maybe the test for divergence if it applies. There are some other tests, but that are more advanced. Maybe we'll get to them if we have time, but for now, this is what we have. Okay, so let's see how we can establish this fact: absolute convergence implies convergence. It seems like intuitive. Yeah, it seems that the stronger, like that to establish the convergence of absolute convergence, it's a stronger property because you have the sum is getting bigger. It's not converging with the aid of this plus or minus signs. But if we want to establish this precisely, then we can argue like as follows. So we suppose that our series is absolutely convergent, then by definition, this means that the series of absolute value convergence. So we have the following inequalities. The double inequality is true. If we take an plus absolute n, then this is non-negative, is greater than or equal to 0, and is less than 2 absolute n for all n. Okay, so first, why this valid? Why this double inequality true? We consider the two cases when an is less than or equal to 0 or an is greater than or equal to 0. If an is less than or equal to 0, then an is negative its absolute value. An is negative absolute n. So an plus absolute n is negative absolute n plus absolute n, so it's 0. And if an is positive, is greater than or equal to 0, is non-negative, then an is the same as absolute n. So an plus absolute n is absolute n plus absolute n, which is 2 absolute n. Okay, so we get that this inequality is valid for all n. Now we apply the comparison test, because we have by assumption that sigma absolute an converges. So sigma absolute 2an will converge. And now our series is positive. The series whose terms is an plus absolute an will converge, because by comparison to the series sigma 2 absolute an. Okay, now we have that this series whose terms are an plus absolute an and the series sigma absolute an converge, but we want to conclude, remember, we want to conclude that convergence. So we want to conclude that sigma an converges. But sigma an is just the difference of these two. Okay? We have two convergent series, so their difference converges, and the converges to the difference. Yeah? Sigma an, you can write an as an plus absolute an minus absolute an. And so it's a difference of two convergent series, so it converges. Okay, this finishes the proof. And now one last thing is that now we have also a new name for series, like we know that this series is absolutely convergent. We have a name for a series that converges but not absolutely convergent. This series is called, a series like this is called conditionally convergent. Conditionally convergent series, so like this alternating harmonic is a conditionally convergent series. Conditionally convergent series are we'll see, will have very strange behaviors. If we, for example, the terms of the series of a conditionally convergent series could be rearranged in any way, in converge to any number you want, or to diverge to infinity or minus infinity. But for an absolutely convergent series, any rearrangement of the terms of the series will converge to the same limit. But for that, we will need another video.